All right, here's 1050 from the calculus workbook sheet on the extreme value theorem. We've got the function v of x is equal to x times 10 minus 2x times 16 minus 2x, and it models the volume of a box. What is the domain of this function, and what are the extreme values of v? So we know that this is supposed to be a real application function that models volume. And we know volume has to be a positive measurement. So I think the first thing I might do is put this function into my graphing calculator and take a look at where this function is positive and grab the domain from there. So let's go to the y equals screen and let's type in x times 10 minus 2x times 16 minus 2x, and see where that leads us if we graph this on Zoom Decimal. All right, I've got some information here, although I'm not 100% sure of the shape of this graph yet. Let's zoom out just a little bit. Zoom out, option 3, and might as well zoom out right there. Okay, well, this volume seems to be positive. I think I can pretty well trace this graph as going up at 0 and then somewhere between 0 and like say 6, going back down and then back up again. And it is a it's a cubic function with a positive first term. So I'm going to zoom back in again. Let's go zoom in decimal, and the domain of this function looks to be everywhere from 0 to 1, 2, 3, 4 to 5, 0 to 5. So the domain, let's get that in here, is 0 to 5. And whether you gave that as an open or closed interval, I think we're going to be all right. Next, what are the extreme values of v? So the extreme values of v we know occur at either endpoints of the domain or they occur at critical numbers inside. So if this is the volume and we need critical numbers, we need to know where v prime of x is equal to 0. And I think what we can do is use the calculator in this case to get that done as well. So let's see, calculator. Let's go to y equals one more time. Let's, inside of y2, have our calculator graph math and then inderiv. So ddx of, I want the function again in y1, and rather than typing the whole thing in again, I can hit alpha F4 and just use the y variable y1. And then I want to graph this at every x value. So let's take a look at the red graph here, and we should see the derivative. Okay, so the derivative is 0. It looks like right at x equals 2. Just to be sure, we can hit the second and then calc and calculate the 0 of this function. Let's see, calculate left bound, how about 1? And right bound, how about 3? And our guess, I'm going to say 2. I don't know. Oh, there were none because we were using, that was the wrong function. Okay, how about this? Close this one down. Graph. There we go. Now let's do the zeros. 2, let's see, left bound 1, right bound 3, and guess is 2. Okay, yeah, it's at 2, so good. So we have x equals 2. Then we want to do a candidates test. So we have our f of x table. We have left endpoint 0, critical number 2, right endpoint of 5. And let's see, if we plug in 0 to v, that's pretty easily going to show us, if a 0 goes right there, we've got 0. F of 0 is 0. I think f of 5, we can prove the same thing, because if a 5 goes into the function, 2 times 5 is 10, and that would be 10 minus 10 would be 0, so this is 0 as well. If a 2 goes in the function, f of 2, we've got 2 times 10 minus 4, so that's times 6. And then 16 minus 2 times 2. So 16 minus 4, that's 8. So we've got 2 times 48. So this looks to me like 96. So our extremes, we have an absolute max of 96 and an absolute min of 0. So this box reaches its maximum volume when x is equal to 2. And this box has a volume of 0 when x is equal to either 0 or 5. And that's everything there.